All right. So today we'll get started with a fresh lecture on Karnaugh map or K map. Uh, so what is it? So far, in the last few lectures or so, we have been discussing ways to optimize Boolean function. All right. We are trying to simplify Boolean function to eventually save on the number of gates, which typically can lead to, in regular sense, reduction in area as well as other metrics, other like performance improvement in general. So Boolean simplification directly lead to hardware improvement, right? So that's why we are so serious about it. That's why we are learning about this all the time. Now, and I tried to point it to you before as well, but this is a slide, uh, you know, based on the textbook argument, and they are now pointing it out that it is problematic to do algebraic optimization. And we probably, I hope that you understood when I was trying to explain this in the class that, hey, given a function, given a Boolean function, here are 4 steps that you can take, but you don't, when I give you an example in class, I'm safe because I know it's going to work. But when you are randomly working in a real life scenario, you don't really know how much simplification you can do with this manual approach, right? Using the algebraic theorems. And also, you don't know whether the output that you have got after optimization is the best. There could be other approaches that maybe somebody else would have taken and arrived at a better solution. Even if you could reduce one more gate, that's a better solution, right? So it was difficult. There are 2 problems. Number one, the procedures are difficult to apply in a systematic way. Meaning, do I apply x plus x prime equals 1, or do I apply the consensus theorem? Like, what should I do first, right? And many people will start with a certain theorem and end up with a certain output, and somebody else will take steps in a different sequence and end up with a completely different output. So it's a little bit difficult to do it systematically, right? There is no defined process. And also it is difficult to tell when you have arrived at a minimum solution. And these are not my comment. And I think I already conveyed my comment when I was discussing those, but these are taken from textbooks. So they agreed with us eventually, right? As you can see. So it's no surprise to us. So what can you do about it? So we need a more, systematic way, something that you can just follow along. I want to also quickly take this small tangent. The more systematic you can make a process, the easier it becomes to code. See that? You cannot just ask the computer, just do what you feel like, try this, try that. No, the computer needs definite, answer. Yes, nowadays with artificial intelligence, they're getting smarter and they're trying to behave more like humans. However, in a regular sense, for any type of software-based approaches, we still need deterministic approaches. So we have to tell the computer the algorithm. So there has to be a core algorithm, and you cannot make an algorithm without defining a system that is repeatable, right? So Karnaugh map is a process that we're going to learn in this lecture, and you will see it's more systematic, more predictable, and you are more almost certain to reach an optimized solution. So is that good? Sounds good to you? So I told you that gradually, as we learn new approaches towards optimization, things will make more sense, and you'll probably like them increasingly because that's how they're, designed. Somebody realized that there is a problem with approach A, so they design approach B. And eventually, when the approach B reached its limit, we have to move to a different approach. All right. So without further ado, let's get started. Before we get started, we have to do a very quick recap, and this is necessary for the class. All right, very quick recap in 30 seconds. Let's do it together, but you have to help me. So given a truth table, I want to get sum of product expression for the function here. And we have done this many times. I know I don't want to repeat myself without necessity, honestly. So let's do it soon. To get the sum of product, what we're looking for is something like this, right? Folks, you understand that? So I should look for the ones only. Are you all good? Okay. So then what will be the term corresponding to the first one? A prime, B prime, C. Could you respond and tell me the second one? Not A prime, because this is 0, and then B, and then C prime, right? And then how about, sorry, How about this one, the third one? A, B prime, C prime. Thank you, please. And this one, A, B, C. All right. So this is a sum of product form. I want to also highlight one key point here. This is, and it was mentioned in the slide. I don't know if you have noticed that. It's also often called canonical sum of product form. Okay. This is basically a universal way of representing any function. This is universal. With these terms, these 8 terms, you could represent any 3-input logic, any 3-input logic in the world. Okay. And the term that you end up with, it is unique. Now, it is not necessarily optimized. You can further optimize it using Boolean algebra, using the algebraic approaches or other approaches. So you could reduce it down to smaller size, but you can start with this canonical sum of product. So I just wanted to remind you of what this CSOP represent, because in this chapter, when you read the textbook, they'll keep throwing this term at you, CSOP, or canonical sum of product form. That's one. And what is canonical product of sum? I hope you now understand. I don't have to go through this, do I? Okay. So what is canonical product of sum? This is basically you have to take the zeros for it, right? And then you need something like this. So you have to take products of sum. There will be some terms inside these brackets, and then you have to take the product of it. So let's do it together. One last time, right? So for the first row, whenever you have 0, for this approach, you take the regular literals, not the primed. Remember, unlike the sum of product, just quickly mentioning, when we were taking sum of product, when you had 1 at the output, to get this, we had to take A prime, B prime, C. So the variables corresponding to 0 were primed, right? For this one, the variable corresponding to 0 will not be primed. That's the approach. So first, we will do A plus B plus C. Okay, and then what is the next 0? This is the next 0. We will do A plus, can anybody tell me what I should do now? B prime plus C prime, right? What is the next 0? A, what did I do? Okay. A prime plus B plus C prime. The last 0 would be A prime plus B prime plus C. And then I have to take product. So this is your canonical product of some form. All right? Very quick recap. I hope it makes sense to us. We are all on the same page. Now, let's move to a different page together. Like I just mentioned, canonical sum of product or product of sum don't necessarily mean the minimum form. What do I mean by minimum form? More optimized, small scale, small sized, right? You can further optimize it by doing something with Boolean algebra. So when you do that, when you go through the steps to reduce it down to a form that you cannot further simplify, okay, that is called a minimum sum of product form, or MSOP. Are you all with me? Okay, why am I mentioning this again? And obviously there will be a similar sister term, minimum sum of product, and the sister term will be minimum product of sum, as you can imagine, right? So MSOP and MPOS, as we just discussed. Okay, why are we highlighting this here? Because using this Karnaugh map approach or K-map approach, what you end up with is always the minimum sum of product. You never get the canonical sum of product. Am I making sense? So the approach that we learned so far using min term and max term, remember in the last few lectures, we have been talking about min terms and max terms. You end up with canonical sum of product and you have to then optimize it. But here is this approach directly gives you the minimum sum of product. Do you like it or not? Is it good? Come on, you can give me your opinion. Does it sound good or not? Like, why not? First of all, if you don't like it, why not? Can anybody comment? I'm sorry, could you repeat that? No, it is giving you the minimum. That's what I'm saying. So the K-map approach that we are going to learn today, right? K-map approach, it is going to give you the absolute minimum sum of product, meaning the optimized per se. So whatever function you get it in the optimized form. Whereas the other approaches that we learn using min term, max term, right? Remember we learned this? They give you the canonical sum of product first, and then they let you optimize it the way you want. So you have full flexibility, but also the full responsibility to do it, right? Are you all with me so far? So if I were you, I would have probably liked it because I will never stop here, will I? If I stop here, my systems will be like huge. I have to definitely reduce it down to a more optimized form. So I needed to do a lot more steps to get to the optimized version. But if an approach directly gives me the most like the optimized version, I would take it. Will you? Okay. Please don't just agree with me for like, okay, yeah, sure. Then you might be in trouble because at some point I'll just behave like, yeah, this is the right thing, and then you'll be caught. Right? You just agreed with me. All right, now please pay attention. I want to show you how to, and this is also more like a recap. Honestly, you have gone through this, but I don't know you remember it properly or if you have thought about it this way. So this is. Can anybody tell me just by looking at it whether it is a canonical form or not? So basically, anything with this ABC, 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 and all these combinations, literal, is typically the canonical form. So you have all three variables available in all the terms. Okay, and then notice after you optimize it, you end up with this expression. I will show you how it was optimized. But notice you don't have all the variables in all the terms. So it's definitely not canonical form. It has been reduced down to something else. I'm not claiming that this is the minimum sum of product, but it is definitely optimized, little more optimized than the canonical form. Are you all with me? Okay. Canonical form is like unrefined sugar. Like literally, you have not done any kind of chemical processing. But after that, you could keep processing it to get different kinds of product out of it, right? So similar to that, this is unrefined. This is basically logic at its raw form, Boolean logic in raw format. And now you're optimizing it this way. So let's see. Once you get this function, and by the way, canonical form can be easily written down looking at the min terms. The min terms basically give you the canonical form. Remember that, folks? So if you have a min term 0, what is min term 0? Remember 0, 0, 0. So that should be A prime, B prime, C prime. And that's what you have here. Can you quickly tell me what is min term 1? 0, 0, 1. So it should be A prime, B prime, C. So you have A prime, B prime, C. See? So min term, max term directly correspond to canonical form. But now, notice, you could then take these two terms, maybe take A prime, B prime as common, and then you get C prime plus C, which gives you 1. So you optimize it down to one term. And you could do something similar to the other terms as well and reduce it down to something that looks like this. Okay, I'm gonna make a point here. I'm coming to the point. We have done this a lot of time already. Okay, what I'm gonna show you for the same function, if you started with a different approach, and the approach is shown here as well. Like you take these two and this two and this two, and you end up with a simpler form. Can you see that? You have 3 terms here versus 4 terms on the other side. So which one is more optimized? Obviously, the one that has less terms. So simply by choosing, maybe you start with this approach, your friend starts with the other approach, and somehow your friend ends up with a better optimized version. So that's exactly the point. How do you know? How do you know? Like basically, it makes sense to me. In fact, you are taking multiple steps, like 4 steps, but still not ending up with the most optimum. And someone being lucky managed to, pair up the terms in a way that somehow led to a more optimized version. Okay, so it's a little bit stochastic, like unpredictable per se. But now between these two forms, which one is minimum sum of product between these two forms? And if I tell you that this is the absolute minimum, you go. So that definitely this is the MSOP, minimum sum of product. Are we all good so far? Okay. Remember, canonical form of a function, canonical form is unique. this is gonna be the same. Like no matter how you're always gonna end up with this expression if you go through canonical sum of product. But minimum sum of product can be different. What do I mean by that? So I will give you an example today. Hopefully, I'll try to finish that today, where you'll see that depending on how you do it, you end up with two entirely different functional representation, but they're exactly identical in terms of output. And both of them will be minimum sum of product. Are you all with me so far? So minimum sum of product could look different. Like, oh, this is minimum sum of product, this is also minimum sum of product, but they are different in terms of functional representation. So how do I define minimum then? Let's see. How many AND gate do you need here? You need one AND gate to calculate this. Two input NAND gate, okay? AND gate, two input AND gate. Another two input AND gate. Another two input AND gate. And then finally, what do you need here? Three input OR gate, right? You need input 1, 2, 3. You have to provide these three inputs to an OR gate. So you need three AND gates and one OR gate. And if you come up with the same number for a different functional expression, that's also minimum sum of product. Apparently, it's all about the hardware. Are you all with me, folks? Okay, just keep that in mind. Let's move on and see what Karnaugh map is. These are all background that was necessary, honestly. Okay, so obviously someone named Karnaugh came up with this idea, and it's not a new idea at all. I mean, basically, I think it was proposed in 1954, if I remember the year correctly. So it's been a while, honestly, more than 50 years, actually 75, if you think about it, right? 75 years ago. So obviously we should have other approaches by now, and we do have other approaches, but this is a really nice and elegant approach. So much so that it is still used, honestly. Okay, so we should care about it. Okay, so K-map, I'm gonna refer it as K-map from now on for the easy mention. And by the way, please read these descriptions that I have, or read the textbook, either ways. I picked and chose the most important sections from the textbook, so that if you don't even have the time to go through the entire textbook, if you go through the slides and make sure you understand it, hopefully you will understand what is absolutely necessary. Okay, there might be something more in the textbook, but I feel like if you understand this, you should be good to go. All right. Now, this is a truth table that we are all used to see. It's not a problem at all. K-map is just an alternative representation of a truth table. So in terms of logical equivalence, a K-map and a truth table are exactly the same thing. The difference is how you represent it in terms of visualization. That's all. A truth table contains the input-output combination for the function, all possible input-output combination. So if you have 0 and 1, this should be your output. It's like a list of things. K-map is also a list of things, but it is organized in a map, as the name suggests. It's like a map. Instead of just a list or a table, it's a map. And it is organized in an intelligent way. And I'll tell you what the strategy here is in a second. Okay. Are you still with me? All right. Now, let me show you. Let's take this analogy simply. Maybe you're looking for coffee places in Knoxville, right? You Google. You just basically Google it and search for coffee places in Knoxville. It gives you a list, like a table, blah, blah, blah. A list. Or you search it on Google Maps, and maps like coffee near me, for example, and it distributes the location in a map. And you see which one is adjacent to where. Like, oh, this thing is adjacent to the other thing. So I can get gas and get coffee like in a quick manner. You see what I mean here? So when you see something with respect to each other in a map format, typically that becomes easier for you to navigate. Versus if I give you a list of things in a tabular format, you don't really know, oh, this place, it might be in the other side of the town versus the other place. So you don't really know the relative position. So that was the thought process behind converting this truth table into a map format. And the way they map things would be by distributing the variables in rows and columns. So for example, let's start with the simplest possible K-map, which is with two inputs. You have input A and input B. You distribute A here and B here. You don't basically see the uniqueness of K-map for two input cases. Okay, that's why I'm going to fast forward a little bit and show you the three input case first, and then we'll go back to two input again. All right, let's see. So imagine you have three inputs, A, B, and C. What you do is you distribute at least one variable in one row, which is say A, and distribute the other two in the second row. You might have question about what if we have four input, five input. Don't worry, we'll cover all of that. Okay. So let's take one step at a time. So A, what are the possible input values for A? 0 and 1. So no brainer. It's like simple. You just list 0 and 1 here. However, the difference comes in listing BC. What are the possible combinations for these two variables, B and C? Let's start with this. Both of them could be 0. Do you agree? Or maybe B is 0, C is 1. Or this is where the interesting thing is, or unique part is. Or I could say this could be 1 or this could be 0. You see about my point here? But we don't do that. Instead of 0, 1 and then 1, 0. By the way, if it were a truth table, we would have done this 0, 0, 0, 1, 1, 0, 1, 1, right? You know that already. But notice when you go from one row to the other, between these two, just one bit changed occurred. Just one bit changed. But between these two, the second row and the third row, you have 2 bit changes. This bit changed and this bit also changed. So both bits changed simultaneously. That's what we don't like. Or at least the K-map folks don't like, okay? They want to move this one out down to 1, 1. Meaning, so if you organize it this way, 0, 0, 0, 1, you have 1 bit change only. And then 1, 1. So between second row and third row, you have just 1 bit changing. And then finally 1, 0. So again, you have just 1 bit changing. You see my point here? Yes, I will answer that. Thank you for asking that question. Of course, makes sense. Like, should we just do because these guys told us to? No. Of course, they had a logic behind it, and we'll see the logic in a second. All right. But first, let's try to get what we are supposed to do. We are supposed to organize these combinations in a way so that only 1 bit changes between the neighbors. Just 1 bit. Are you all with me? Is that a difficult thing to do? No. Just, change the orders of few things. If there were more variables, of course, it will be difficult to track a little bit, but you'll get used to it. Okay, so notice 0, 0, 0, 1, not 1, 0. We do 1, 1, and then 1, 0. What is the reason? Because we want to make sure just 1 bit changes at a time. Is that okay for you? And I promise that I'll explain why we do this, okay? And it will make sense after we go through the process of K-map, and I'll show you that's why we did it, okay? All right, but for the timing, bear with me. With this, I'm gonna distribute this truth table into this K-map, and we'll do it together. But you have to pay attention, all right? Ready for it? So I'm going back to my original slide, this like the single variable one, and then we'll go to the 3 variable one. So instead of 3 variable, let's go back to the 2. And because it's easier to explain, you see? So with variable A, you have 0, 1. With variable B, you have 0, 1. That's why you don't see the difference here. Basically, you don't have, anyways, you have just 1 bit changing. Okay. What we're going to do now is distribute this truth table into the K-map. Notice, just look at the ones. Just look at the ones. Okay. When do you have 1? For the case where both A and B are 0. So think of plotting something in a Cartesian coordinate system. You need X and Y, and then you put the point at the XY point, right? Does that make sense? So similarly, what is our X and Y here? What is the coordinate? 0, 0. So for A0, B0, I should put a 1. You see that? See my point here? Okay. Similarly, where is the other one? This one. For A0 and B1, this is A0, this is B1. That's why we put a 1 here. And then the others are 0. So we just populate this K map with the truth table inputs. Like I told you, it's essentially the same thing, just presented in a different way. Still with me? All right. Now what do you do? Notice, look for adjacent ones and merge as many ones as you can. If you have like 2 ones side by side, take all of them. 3, take all of them. 4, all of them. So it could be either horizontal or vertical, right? As long as you have horizontal or vertical, just take them together. So basically merge this together. You see that? This is illustrated here. And then what? I'll tell you what. But do you see what we are supposed to do? We are supposed to group them together, as many ones as we can. So notice we managed to group 2 ones together here. Only horizontal or vertical, okay? Either vertical or horizontal, not diagonally. All right. And everything will make sense. Don't worry. I'll explain the reason. Okay, now once you do that, just notice in a column format, when you look at these 2 ones, there is a variable that stays the same and doesn't change, and another variable changes. What is the variable that doesn't change? There are 2 variables here, right? A and B, of course. Which one doesn't change along this column? A doesn't change, right? You see my point? Okay, A doesn't change. So basically, what you have to do is take the variable that doesn't change, which is A here. And what is the value corresponding to A? 0. If you have 0, you have to prime it. If you have 1, you don't have to prime it, just the variable A. So this is your functional output, if equals A prime. Again, I know, I'm just telling you what to do. And then I'll explain. I'll take a step back and explain. But do you get it? Like basically just looking at the map and grouping the ones together, you can point out the variable that doesn't change and see whether it's 0 or 1. And you basically just act accordingly. If it is 0, just prime it. Done. Now, here is what we're trying to do here, honestly. Let's see. Okay. Just looking at this truth table, right? If we were to do it the old-fashioned way, the one that we practiced together, we would have looked at 1 and tried to make A prime, B prime. Do you agree with me? And then I would have looked at the second one and would have done A prime, B, and then plus. All with me? All right. Now, notice, what would be my next step to optimize it? Looking at this expression, what is common between these 2 terms? A prime. So I would have taken A prime as common, and B prime plus B would have given 1. So apparently I would have been left with A prime anyways. So notice, what you can take common is represented by the map in a way that the ones could be grouped. You see my point here? So I told you, look at the variable that doesn't change. Why? Because that variable could be taken common between multiple terms eventually. That's how the map is designed. So when you have ones grouped together, there will be a variable that will not change between these. When you have rows and columns, along the column or along the row, something stays the same. That's the beauty. So you could easily point out which variable to take common. All with me? All right. So I know it's super simple for a 2-input case. So let's do something for the 3-input case together. Ready for it? Let's do it. Okay. By the way, what do I mean by this position? I hope obviously you don't have to memorize it. It should be easy for you to like understand after you practice a few times. All right. So when you do this 3-input case, you distribute A along one, like either row or column, and BC along the other. And I just want to point out, you don't have to do it this way. There might be a question. What if I do A this way and BC the other way? It's fine. No worries, you could do it. Okay, but you have to be mindful of how you're distributing the values. So for example, A is 0, A is 1 here. And for the BC, you have 0, 0, 0, 1, 1, 1, 1, 0. Now, tell me something. I want to take this row and somehow show the output. 1, 0, 0. What is the value of A? Sorry, 1. So I should look at this column. And then 0, 0, I should look at these rows. So this is your 1, 0, 0. Does that make sense? But when you change the variables, like put A here and BC there, this will no longer be that point. It will be somewhere else, but I hope you can still find it, right? Does that make sense? It's okay. We will go slow. We will make sure we are all together. So let's take another example here. Let's take this one, 1, 1, 0. Let's do it quickly this time. What is A? 1. So I should look for this column. What is BC? 1, 0. Where is 1, 0? This is 1, 0. So this is the square that I should look for, 1, 1, 0. And remember, these values will not be given in the K-map. You have an empty square. So you have to look for it yourself. And we'll do it right now. Let's do it right now. So let's draw. This is exactly how the K-map will be. Empty squares. So you have 4, you have A here and 0 and 1. Then you have BC here, basically 0, 0, 0, 1, 1, 1, and 1, 0. Oh, what did you do? Okay. Are we all good so far? Okay, let's see. Now, I'm gonna try to distribute ones, just the ones. You could also do 0, because wherever there is no 1, there will be 0. So just be mindful. If you have, imagine if you have a truth table where there are like 6 ones and 2 zeros, which one should you try to put, 1 or 0? Try to put the zeros because there are less of them, and then rest of it will be filled with 1 anyways. So just to speed up the process. But this example is chosen in a way deliberately that you have equal number of zeros and ones. So doesn't matter. Am I making sense here, folks? Okay, so let's try to distribute the ones. So 0, 0, 1. Let's try to do it. A is 0. So let me change the color here. This is A 0. And then 0, 1. Where is 0, 1? Right here. So I should look for this point. Are you all with me, folks? Okay. And then what is the next one? This one, which should be 0, 1, 0. This is my 0 and this is my 1, 0. So this is 1. Can you try doing the third one? 1, 0, 0. So 1 would be this one and 0, 0 is here. So this is my 1. And finally, triple 1. 1, 1, 1. This is 1, 1, 1. Okay. And rest of it will be 0. Any problems so far, folks? No. All right. All good? Okay. Few important point that I will make now. Yes. Great question. Great question. We could also do product of sum as well. But mostly when you use this K-map approach, you like when you get the functional output, you always end up with sum of product. Okay, so that's a very important question. But you could always represent both product of sum or sum of product in K-map format. But you have to just, I told you that basically one versus the other. I'll show you like basically in one of the examples. If you're given a product of sum instead, how can you distribute those values in a K-map? But remember, the K-map always gives you the sum of product, not product of sum. Okay, but you can map both of them in a K-map. And honestly, personally, I think it's easier to deal with sum of product anyways, because product of sum typically gives you, remember, larger functional output. So you have to further simplify it anyways. So, all right. By the way, what is this figure doing here? The purpose of this one. Oh, by the way, before I erase it, I want to show you this. Somehow I chose this truth table in a way that you don't have any ones grouped here. You see my point? You see any one adjacent to each other? No. So that means, honestly, going through this K-map, you'll not be able to optimize much. Okay, you will end up with basically what you'd have gotten with conventional mean term expansion, simple mean term expansion. Okay, are you all with me? By the way, since we somehow managed to get this unique combination. Let me show you what to do with it. Okay, you have gone through the process of mapping it into a K-map. And now you're saying like, oh man, there is no way to optimize it anyways. So I have basically wasted my time. But how would I know without mapping them first, right? Okay, so the function would be, ready for it? Just look for the ones. Since you cannot group them together, you have to take them separately. Okay, look for the one. So for this one, what is A, folks? 0. So you have to prime it. And then what is BC? 0, 1. So you have to prime B and take C regular. Are you all with me? So since you cannot group them, you have to take them individually. So what is this one? Plus. This one represents A0, that means A should be primed, and BC would be 1, 0. So B is unprimed and C is primed. You see what I'm doing? I'm doing exactly what we used to do with these rows. Didn't we? So this K-map is not giving you any advantage here. If this only makes sense if you could have ones grouped together. Otherwise, you're going to end up with exactly the same function as the min terms and max terms used to give you. Are you still with me, folks? Okay, so there is no guarantee that simply because you went through the process of remapping a truth table into a K-map, you get a better optimized solution. Because if you cannot group the ones, that means that was the optimized solution. Right? That was the optimized solution. You have no other option. Okay. By the way, what is this figure doing here? This figure, in case you are curious, this is how the min terms are distributed. All right. So what does 111 mean, folks, in terms of decimal? 7. So notice this is 7. That's exact. This is M7, min term 7, right? We have done this together. So min terms, this is how in case you are curious, and this is not just for curiosity, by the way, right? Sometimes if I give you a function in this form, let's see if you can do it. Okay, can anybody draw the K-map for this function? What do you do? This is much simpler now. Where is 1? This is 1. Let me use a different color here. So these are position. These numbers represent min term position. So min term 1 is here. So you should put the 1 here. Where is min term 2, folks? Can you look for it? Right here. So I should put another 1 here. Where is 5? This is where 5 is. That's how you distribute it. But you don't basically memorize it. Honestly, if I were you, I would have just converted it into like 0, 0, 1, and this would be 0, 1, 0. It is much easier for me to track them rather than 1, 2, 7, 5, right? Because that's not obvious. And just notice how random these things are. 0, 1, 3, 2, 4, like it's totally random. So there is no way for us to memorize. And wait until you see the 4 input and the 5 input one. So anyways, just deal with binary, folks. That's going to make your life simple. All right. Why are you sad? Are you sad for some reason? You seem very silent. Okay. Don't feel bad if it is things sound boring honestly at times, but don't worry. We'll move into more interesting stuff gradually. But we cannot just jump there. Okay. We have to go through some excruciating process first. Okay. So another example. Ready for this? Okay. So this is a function. Now we're going to take a different route. What if I give you a function instead of a truth table? Right? I showed you, if I give you a truth table, you can map it. If I give you the min term example, which I just showed you, you could map it. With the min term positions, you can map it. Now, there is another way to represent a Boolean function, which is just a functional representation. Let's see how we can map it. All right? Let's do it. Okay. So basically, you have A, B, C, and this is explained here. This is directly taken from the textbook, honestly, this example, because I liked the way they explained it. So you could just read it later on. I'm going to explain this myself. So if you have A, B, C prime, oh, how do I know how many variables I have? Sometimes they mention it right away if they're very good. So you have 3 variables. You distribute them across rows and columns exactly the way you discussed. Okay. If they don't mention specifically, spell it out that you have 3 variables, look for how many variables you have, how many, literals you have. You have A, B, C prime. So that's it. You don't have D or E. So that means you have 3 variables. Okay. All right. So because there will be missing ones. Like this one only has one, but somewhere there is a C, somewhere else there is a B. So that means total, you should care about 3 variables. All right. Now, A, B, C prime is 1. Can anybody tell me when this is an AND relation? An AND function gives you 1 when all of the terms are 1. Are you still with me, folks? So when will I get a 1? This is important, and this is a little bit different than this is not as straightforward. So you should definitely pay attention to this. Given a functional representation, it is a little bit more tricky to represent it in K-math format versus a truth table. So you should pay attention, all right? So A, B, C prime. When will this particular term give you a 1? Tell me. All of these terms, this should be 1. That means A should be 1. And B should be 1. Do you all agree? And how about C prime? C prime should be 1. That means C should be 0. So C should be 0. So I'm looking for A equals 1, B equals 1, and C equals 0. Where is that location here in the K-map? A equals 1 is here. B equals, I'm looking for BC 1, 0. Where is 1, 0? This is 1, 0. So this is the one that this is the position that I'm looking for. And I'm going to put a 1 there. And that's ABC prime. All with me? Okay. How is it like different? Well, you'll see the difference in the next time. All right, wait for it. Okay. Next, for the B prime C, folks, B prime C. When is B prime C 1? When C is 1 and B prime is 1. B prime 1 means B is what? 0. So in terms of B and C, I'm looking for 0, 1 combination. But how about A? How about A? I don't know, because I don't care. Even if A is 0 or A is 1, for both cases, since A is not even there, it's a don't care case for us. So basically, as long as you have 0, 1 for BC, I don't care whether A is 0 or A is 1. For both cases, I'm going to put 1. You see that? All right. So this basically represents this B prime C term. And finally, we have a few minutes left, thankfully. Finally, this term. So the less you have, the more it covers actually, all right? So A prime, when is A prime gonna give you 1? Or A equals 0? Because A equals 0 means A prime is 1. So I don't care about B and C. Like whatever the value of B and C might be, as long as A is 0, you're gonna get 1. Okay, so what does that mean? This is where A is 0, and I don't care what BC is. For all of these cases, you will have 1. So you'll populate it. I know what you might be thinking. Hey, we basically filled this location twice. Doesn't matter. For different terms, I might have to fill the same location with 1 and 1 and 1 and 1 over and over again. Doesn't matter. You know why? Because 1 plus 1 is what? In Boolean. It's not 2. It's what? 1. And 1 and 1 is what? 1. So there are multiple ways to make a location 1. We don't care. Are you all with me? Okay. So that's how you map a function into a K-map. So once you have this K-map, now let's see how to optimize it. See, you can group these 4 ones together. Can you not? Wonderful. What is common? Basically, within all of this term, which I told you this, which variable doesn't change here among all of them? A doesn't change, right? Are you all with me so far? Okay. So, and what is the value of A corresponding to that column? 0. So I should take A prime. So that covers all of these ones. Remember, you have to cover all the ones that you see in the K-map. If there is one left out, you have to cover that individually without a group. As I showed you in the last one, we couldn't group anything together, so we had to cover the ones individually. So Have I covered all 4 of the ones? Okay. We are not done yet. I'm going to show you something. By the way, among these 4 rows, there is a variable that doesn't change. Is there any variable that doesn't change? Is there a variable that doesn't change? Notice. Well, B changes from 0 to 1. C changes from 0 to 1. You see that? So we don't have any variable that doesn't change. So you're good. I see some confused faces. Yes. Yeah. Oh, yeah. Okay. Let me repeat that. All right. So you start with 0, 0, 0, 1. No question about it. Right. But our strategy is to change just one variable at a time. So if I put 1, 0 here, both variables will change in one step. So that, yeah. So does that make sense? All right. So that's what, by the way, we are out of time. So let's do one thing. We know how to map it into K-map. All right. So this is the slide where we'll begin in the next class, and we'll just convert it into a function, and then we'll move on to the last couple of slides. All right. So no rush. Thank you.